In a prior film, you learned that to achieve the strength of flux and magnetic fields, the AC generator was designed with electromagnetic poles created by an excitation voltage of direct current, which was supplied to the rotating coils through a system of collector rings and carbon brushes mounted on the rotor shaft. The source of DC power was called the exciter, and although the exciter is not actually a part of the AC generator, it is so important to the control and proper operation of the generator that it must be studied as part of AC generators. But first, let's do a little review. For instance, magnetic fields or flux lines are created when an electromagnet is energized with direct current. If a coil is moved through these flux lines, a voltage is generated within the coil. And as the direction of flux lines change with respect to the coil, or as in this illustration, the moving coil changes position in relation to flux lines, the voltage changes direction. It is called alternating current. If the current flow of the DC supply is increased, magnetic flux will become stronger or more dense. The rotating coil will pass through more flux lines, and the result is an increased output voltage. Correct control of DC or excitation voltage to the rotor not only provides the magnetic fields needed to generate power, but can effectively change the AC generator output by increasing or decreasing flux. It takes a lot to properly excite a large AC generator. Several thousand amps of direct current may flow in the rotor windings to create the flux densities necessary for full output. An excitation system for such a unit is one large DC generator with a series of controls and monitors capable of supplying the correct DC power level to exactly balance the AC load requirements at any given moment. The current produced in any rotating generator will be alternating. The requirement here is to obtain non-alternating or direct current. How? Well, a simple rotating coil within a magnetic field is connected to fully circular rings as shown. Output voltage will be the same as the coil voltage, an alternating current. But if one ring is split in half, connecting one coil lead to each half, the brushes will contact a different ring section, each 180 degrees of coil rotation. This then becomes a rotating switch, which reverses connections in exact step with voltage changes, in other words, a DC output. This is a graph of voltage generated by these two units. The DC is called pulsing power. Coils are at points of greatest voltage as shown in this voltage pattern. Large AC generators produce their power output in the stator windings, not in the rotor, as shown here. In DC generators, however, the rotating element is utilized with split rings to create power output. To reduce power losses and heat in the AC stator core, a laminated construction was used. A DC generator also creates alternating voltages in the windings, so the same type of laminated construction is used in the rotor. DC rotor windings are made in the same way AC phase windings are, that is, with transposed conductors of pure copper, then shaped, insulated, and physically locked into the rotor slots. These are usually called armature coils. For the same reason an electromagnetic field in the AC unit is used, the poles or field coils of the DC generator will be electrically magnetized and controlled. DC voltage excites the field coils. Once a DC voltage is generated in the rotating coil circuits, connections can be made to the field coils. These are self-excited fields, but as the output voltage increases, with speed of rotation for instance, more current is forced through the field coils, creating more magnetism, which in turn creates more voltage output, and on as long as the mechanical energy driving the unit can supply necessary forces to rotate the coil loops through the heavy flux lines. Eventually, however, the changes in excitation currents have less and less effect on the power produced by the rotor windings, since flux lines reach a point of saturation. At this point, generator voltage levels off. Strong electromagnetic forces affect the soft iron within the field pole piece, and it usually retains some magnetism even when no current flows. In a self-excited generator, this residual magnetism is enough to create a small voltage when the rotor coils move through these flux lines. If the voltage generated is initially enough to overcome resistance in the field, current flow will increase the magnetism. This starts the rapidly rising progression until the poles are again saturated. Control of voltage output of the DC generator will depend upon the number of rotor coils or windings, the speed of rotation, and the strength of the field or flux density. Once the generator is built, little can be done to change the number of coils, which must be through electromagnetic poles. This is easily accomplished by placing a variable resistance or field rheostat in series with the field windings. Increased resistance and reduced current flow in the electromagnetic coils lower the flux density. Therefore, less output from the generator. Decrease the resistance, power output rises. Many generators have one or more additional fields which affect the magnetism of pole pieces. Study this schematic a moment. This schematic shows rheostat control of the main field windings, or shunt field. But if the entire current output is passed through a second field, a field in series with the output, which adds or subtracts flux according to current flow, a second control is realized. Generators with a series field are called compound generators. For more accurate and rapid control, the DC generator may have another small magnetic flux in the main DC generator field. The control field has its own DC power supply. This is often called a motor generator set, controlled by a complex instrumentation system, which sense demand changes in a system and can control the excited voltage with long time lags caused by inductance of the highly magnetic shunt fields. The mechanical energy which causes rotation, together with carefully controlled flux fields, are necessary for the AC unit to function effectively as the loads change. Loss of the DC field, even for a very short time, can cause serious voltage disturbance possible to the generator. The exciter must have a reliable source of power. Often the exciter is driven from the main generator drive shaft, called a shaft-driven exciter. Like most DC machines, exciters will require more frequent maintenance than AC equipment. Brushes, slip rings, switches, and other parts must be checked often. To service a shaft-driven exciter, it may be necessary to shut down the entire system, and in many installations, the exciter is totally independent of the main generator. Frequently, it is driven by an AC motor and includes a large flywheel which continues to provide a continuing rotation in case of momentary interruptions of AC power. A second, separately driven DC generator unit is often available, as the unit can serve as standby for all exciters. Normally, an exciter will feed only a single AC generator, so it can react rapidly to the requirements of that generator's output at any given moment. However, because the controls in an excitation system tailor the DC voltage to fit the needs of the AC generator, exciters can be used on many different units, one at a time, if the output rating is sufficient to supply the AC unit. To connect and disconnect the exciter to the main AC generator field, a special circuit breaker field switch is used. But opening a highly inductive circuit such as the AC generator circuit is another matter. The dense magnetic flux created by the DC will suddenly collapse when the switch breaks the current flow. Where these force fields collapse, the flux lines move through the rotor windings, creating sudden and very high voltages in the brief period of collapse. We call this induction. Inductive voltages can create some truly shocking voltages. Your auto uses this phenomenon, in fact, to create the high voltages needed to force a spark across the spark plug gap. The coil in a car contains two sets of windings, closely surrounding a single iron core. As the battery feeds in current at 12 volts, the primary coil gradually creates a strong flux field held within the core. Now, if this current flow is broken, the suddenly collapsing lines of magnetic force will induce a voltage in the second coil. Since this coil has several hundred times more windings than the primary, the voltage will be quite a bit higher. The exciter generator acts like that primary circuit when its field collapses. A sudden and high voltage is induced in the coils and seeks to keep the current flow by actually jumping the switch's air gap. The field circuit breaker then must absorb the back effect or kick of the field coils and also prevent or reduce the arcing caused by highly induced voltages. We can reduce this high voltage arc by slowing down the collapse of the flux field. Suppose, just as the main breaker contacts are about to part, another set of contacts closes to add resistance in parallel with the main generator field circuit. When the DC contacts open, field currents still flow through the resistor. This flowing current in the charged field coil permits magnetism to decay slowly, and very high voltages are not created. Like the tire on the right, a sudden release of pressure can be serious. If pressure is gradually released, there are no shocks to the tire. The discharge resistor acts as a bleed valve to prevent high and sudden voltages in the generator system. Even without the effects of induction, DC voltage is harder to will extinguish itself rapidly when the zero voltage is reached. But with DC, a high enough resistance to stop current flow completely must be developed. The arcing time is considerably longer, and during this time, current crosses the open switch in an arc effect and must be quenched as rapidly as possible. The DC circuit breaker may include special arc chutes and magnetic blowout coils, which draw the arc into a long, interrupted path, stretching and cooling it. More about these devices, however, in a later lesson. One word of caution here. Only a circuit breaker designed for DC service should be used on DC circuits, and specially selected breakers should be used with inductive loads or high power circuits. One DC switching device which is critical in the operation of the exciter is the ring and brush which converts the generator's AC output to direct current. This circle of ring sections surrounding the shaft is usually called a commutator. The direct current from the exciter is fed into the rotor field windings of the AC generator. This is accomplished by slip rings, usually constructed of steel, and carbon brushes. Brushes on both commutator rings or slip rings must be kept clean, free of oils and grease, or any foreign bodies which would reduce the easy flow of high currents. The spring pressure which holds the carbon must be properly set and maintained. Cooling is important also in the brush area. Grooves in the rings permit cooling gases to circulate under the brushes. Various other methods are employed to keep the rings, brushes, and brush rigging from overheating under high current loads. The operation, control, and maintenance of the exciter and its related equipment will be developed in a later lesson. Okay, it's time to open your booklet to page 4 and answer the questions. When you finish this quiz, start the machine and we'll check the answers. Okay, let's go over the answers. The first one is true. It makes little difference whether the wire or the magnetic field moves. The result of the flux motion with respect to the circuit wire induces voltage. The second question is also true. The exciter, a DC generator, generates a voltage in the rotating coils, which by means of the switching effect of the commutator and brushes is changed to direct current. The unit will be smoother if more coils and/or poles are used. As coils or poles are added to the DC curve shown here, it will flatten or smooth out. False for number 4. Since the pole pieces tend to maintain a residual magnetism, the generator will begin to produce current as soon as it's restarted. This effect will continue to build up in the field coils until they're saturated. A key point, number 5, and it's true. If you remember these 3 factors which affect the output of a DC generator, understanding of excitation systems will be easier. If you said number 5 is true, chances are you also answered number 6 as true. Current flow in the field coils creates the magnetic flux, a key method of controlling the generator's output voltage. That important field current flow can be controlled by changing the resistance of the coil circuit with an external variable resistor, not a capacitor. So number 7 is false. Question 8 is also false. If the excitation voltage to the AC generator rotor coils is lost, even briefly, the generator will not only be unable to produce electrical power, but real damage may result in the generator. 9 is false. Although shaft-driven exciters are fairly common, the separate unit is more desirable because it can be maintained without shutting down the entire turbine and main generator system. Number 10, false. Even without induction in a DC circuit, the flow of current does not stop until the arc resistance becomes too great for the voltage, so special DC switches are always used. 11 is true. The flow of current through any conductor, including rings and brushes, generates some heat. As the flow increases, so will the heating. Just because the AC rotor is not moving does not mean the exciter can't energize the field, so number 12 is false. In fact, there is danger of great heating damage to the rotor if the exciter does apply voltage to a non-moving coil. 13 is false. A reserve exciter can be used with any generator where DC requirements of the rotor coils can be met by a reserve unit. 14, true. All generators must create power as AC flow. On the exciter or any DC generator, this AC generator power is switched to direct current by the commutator and brushes. Number 15, false. Although the output in cross-compound generators is linked, input to each rotor is normally provided by individual exciters. There are simple exciters such as the battery and complex rectifier systems. DC power and some means of control is all that's required. Well, now that you've learned something about how to generate AC power with an electromagnetic field and rotary motion of power, and further how to control this AC output by controlling the voltage of the DC field coils, you have the real fundamentals necessary to understanding the generation equipment in electrical power plants. In the next several lessons, we'll begin to examine what happens to the electrical power now that it's generated. As always, you may repeat this film if you like, or continue with the next lesson.